Hello, this is my video lab report for Lab 4. In this lab, we're going to observe the motion of an oscillating object and compare it with a model that we're going to create based on the momentum principle. We'll also analyze the object's motion in terms of the energy principle to test whether the two principles are compatible or not. This is the motion that we want to observe and analyze. In order to extract the observational data, we use tracker. As you can see here, we set the origin to be at the fixed attachment point, and we calibrate the length of the spring to be 0.7 meters, which was measured independently. To collect the data, we capture the center of mass of the object at each frame of the video. To create the model, we need to set the initial conditions that we get from the observational data, specifically the position data, and we set the initial velocity to be 0 since the object is released from rest. For our model to work, there are some constants that we need to calculate. First, the spring constant, which we can derive from the equation above. Second, the relaxed length of the spring, which we obtain by considering the static equilibrium state of the spring, where the gravitational force is equal to the spring force. We set the two forces equal to each other and solve for the relaxed length of the spring. In the segment of the code above, we implement the momentum principle to update the position of the object. In this model, we're assuming that there are only two forces acting on the object, the gravitational force and the spring force. We use the momentum principle to model this scenario because it provides us with a convenient way of updating the position of the object. The code below shows the implementation of the energy principle. Here, we're considering the system to be the object, the spring, and the earth without including anything in the surroundings. From the energy principle, we know that the total energy of the system is equal to the sum of the total kinetic energy and the total potential energy. Here we can see how our model's prediction compares to the experimental data. On the x position, the model is a little bit delayed. On the y position, the prediction is even less accurate. We can see the delay in the model's prediction gets larger after each oscillation, and the predicted amplitude is greater than what it should be. Some of the possible sources of error include neglecting the effect of air resistance, assuming that there is no motion along the z-axis, and inaccurate collection of the data. In order to improve the accuracy of the model, we make account for all relevant forces and directions, capture the center of mass of the object more accurately in Tracker, and use a camera or analyze a video with a better or higher quality. This is the energy graph of the model. By looking at it, we want to know if the energy principle is satisfied or not. As a reminder, the system we're considering in this model includes the object, the spring, and the earth, while the surroundings don't include anything. Since there's nothing in the surroundings, the system's energy can't be changed by the surroundings, meaning the change in energy of the system, delta E, is always zero. In this graph, we can see that it's true, which means that the energy principle is satisfied in this model. Next, let's compare two different ways of calculating the period. If we consider 4 oscillations in the x direction and find the average time it takes to complete one oscillation, we get the value of the period to be equal to 1.643 seconds. But if we do that for the y direction, we get 1.524 seconds. One possible explanation of this difference is that the y direction is affected by the force of gravity, while the x direction is not. This might have caused the spring to oscillate faster in the y direction. In conclusion, the energy principle is compatible with the momentum principle, and the two principles don't conflict with one another.